experience here about big data solutions, and it's great that we have Ben here as a keynote. Okay, let's give a round of applause for Ben.
Everything's okay volume-wise? Great. Thank you all so much. My name's Ben. Up more. Volume. No, I'll just try to project. I'm going to be talking about density, the not-so-secret trend driving the future of data analytics. And I've had a hard time starting this talk or trying to get into what density is, or what it's, I think a lot of people think of density, or what I think of computational density. So instead, I'm just going to try and motivate this with a thought experiment. So many of you are familiar with this large language model called Llama 3.1 405B. 405B. It feels a lot like I'm talking about genetics. And can I reproduce this model with less dense, less powerful hardware? So this model was built with 15 trillion tokens. I think it's around 40 terabytes of data. It took 30 million GPU hours. It was executed on 16,000 H100s. These are GPUs that have 80 gigabytes of GPU memory. They're around 4,000 teraflops for FP8 performance. Very, very powerful machines. And I want to ask, could I reproduce this using lower end hardware? L4s are kind of the next T4s. You can go get these on Colab. They have a tenth of the memory space. They're around 3.5 times slower than an H100. And the answer to this is that I actually haven't given you enough information. That you can't even begin to start asking this question because computers are actually a lot more complicated than just these individual stats that we sometimes rely on, which we can make useful decisions about. But I'm not telling you about how we're pipelining data to the GPU, or how I'm pipelining data from disk to RAM to the GPU, or how the GPU itself is actually getting data from GPU memory onto the compute core. So all these things collectively is what I'm going to refer to as density. So it's not just the CPU cores in your machine. It's not just the total RAM. It's the memory bandwidth. It's the amount of GPU cores. It's the memory bandwidth within these devices as well. And we're going to look at density in a nonlinear, hopefully mostly correct, imperfect timeline. It's not a timeline. And think about how hardware and software and data, these three things, are constantly co-evolving and colliding and pushing on different groups to do something different, right? If one starts expanding or exponentially increasing in a dramatic way, the other two typically have to accommodate. We'll see things where software leads, things where hardware leads, and things where obviously data has exponentially increased. And everybody in this room has probably, well, shoot, maybe there's like some 15 or 20-year-olds here who didn't feel the things that I felt. We're going to jump to, okay, while we're talking about stuff, I'm also going to think about like how we build tools. And I think about, I like to think of myself as a tool builder. I think about, is this tool trying to accelerate the novice? Is this tool requiring a lot of education on the part of the user? So not to brown nose too much, but Excel is arguably the greatest data analytics platform that's ever been created. It onboarded a whole bunch of people who knew math, who knew how to do some tabular kinds of things, and allowed them to go about their day. These ideas are older than Excel. These ideas of sheets actually extend further into the 80s and 70s, probably the 60s. But Excel figured out the right kind of interface. And I think that's like a great shining example of accelerating the novice. And all of us here are trying to solve all sorts of problems. We're tool builders at different levels, either deploying LLMs or writing deep mathematics in Python and C++. So we'll start classically at the ancient Greeks, or actually this predates ancient Greece. This is 1400. This is a tablet that's written in a language called Linear B. comes from the Mycenaean kingdom. It's a place in Knossos on Crete. And I really like this as an example of tools. Obviously, we figured out humans how to put clay together. I think it was only baked into this tablet because the palace burned down. Scratched some writings on it. And this tablet translates to administrative records. It's actually a really boring tablet. But maybe all of our jobs are actually really boring as well, because what this is like, not to be too grand, but kind of, it's a database. It's actually just a record of what the kingdom had. How many goats, how many sheep, how many footstools, how many lamps. And a lot of these problems that we're solving today kind of look a lot like these things. What do I have today? I need to count the things that I have today. What am I going to have to do tomorrow? I'm going to have to do some stats or some math on it. Obviously, the tools increase, the measurements that we're doing increase, but kind of all problems reduce to this. And we're going to see a lot of these kinds of cycles throughout this talk when we talk about density and scaling out and everything. So we're going to jump to the 60s. Fortunately, I don't have time to go over mechanical Turks or digesting ducks. We'll skip way past that and everybody else and land right into this tumultuous, chaotic, but really cool world of the 60s and 70s, where people were playing with different kinds of hardware. The IBM 360 was the machine to get. Probably a lot of people here have heard that term. You won't get fired if you buy IBM. This is when all those things start to happen. They are very successful at building production machines that are very useful for everyone. And at the same time, people at this other corporation you probably never heard of, called CDC, start exploring the world of parallelism. I have one machine, now I want two. Can I go twice as fast? And a whole bunch of things fall out in that one grand experiment in the 60s of trying to do two things at once. What kinds of things were those? SIMD applications, parallelization, a whole bunch of computer science and computer engineering get created. The Cray one on the right is a very classical example of a supercomputer. And a lot of these things, a lot of these machines have storied past and people that worked on them. Amdahl from Amdahl's Law worked on and designed the IBM 360. The CDC 6600 was built by Seymour Cray, who then went on to build the Cray. Like, there's all these really great, wonderful stories in our collective computing history. But what was the software that we ran on these machines? This world was extremely chaotic. We're figuring things out. The US government, I assume every government in the world, is funding all sorts of projects to go after any number of problems. And there's a bunch of specialty hardware that's created. There's compilers that are created, which lets me build higher level languages and compile them down to machine code, and everything is done in assembly. We've gone way past the print cards. And we start thinking about how to actually approach different tooling. Should I build, if I want to make embedded systems, do I need to build everything from the ground up? How do I teach the next engineer who has to work on this machine how to manipulate it? And very quickly, people don't want to do that, right? They want to accelerate the novice. I want portability in my software. I want my Fortran, my COBOL to run on the IBM 360, and I want it to run on the Cray one. So a lot of the things that we take for granted actually had to be, unfortunately, like invented. It had to be learned. You had to go through that process that cycle of learning how to build tools for one another. And what you see on the right is this Tower of Babel representation of just how varied those languages were. Many of these things I've never heard of. I think usually in these slides people like to have a family tree of languages. These things map to Algol, these things map to Fortran. And I like this one because it shows just how much variety there was in trying to achieve some kind of unification that just wasn't there. Maybe it still isn't there now. Incidentally, this image appeared in Jean Samet's history of computers that she wrote in the 60s and 70s, and she is a little bit of an unsung hero. She's one of the co-authors of COBOL, along with Grace Hopper. So speaking of Grace Hopper, a little bit of a transition problem. She gave a set of really great talks in the 80s. And a lot of people here, I'm going to probably do this a couple times in this talk, but you've probably heard any number of times, data is increasing. Data is the oil. Data is all these things. And even in the 80s, we have been saying these same kinds of things. What I especially like about this quote from Grace Hopper is that she notes not just that the data is increasing, but the demand for instant access also increases. So that's a little bit of nuance, but not something I hear as often. So in her day, instant access was things that were online, as opposed to like in batch. You had to physically go and take the media onto the system. In today's world, we're still solving the same problem. Those solutions look a lot like binary formats, maybe like Parquet, which is a little bit of a more modern binary file system. Or there are things like data lakes and data warehouses. We still are iterating on this problem. We're not going to have any solution. There's never going to be any one solution for anything that I'm about to describe. We're just going to keep on iterating and going around this cycle any number of times. And hopefully that's not depressing. Hopefully that's really exciting for you. Because it's a fun ride. Like, you get to go and experience and build this next iteration, but it's not, for the next generation, going to be a solved problem. Excuse me. So, sorry. I'm just very excited about this machine. I can't tell you how many hours I spent reading and watching videos about this particular machine. It's called the connection machine. It was a great, wonderful experiment that happened in the 80s from a graduate student who was at MIT named Danny Hillis, who had this wonderful idea of taking low-end hardware and packing it all together. This was a massively parallel machine. It was built out of, I think in the first iteration was 2 to the 16-bit processors. So thousands, massive, like many thousands of processors all working together to take these SIMD ideas that were being explored in the 60s and 70s and go after a new problem. They thought of this machine, they built it as an AI machine. It was designed by Tamika Thiel and Maya Lin. They had a working relationship with Steve Jobs. If you know the next computer, it looks very similar to that. And Richard Feynman worked on it. It had like a bunch of really kind of amazing people working on this machine to go after their problems at the time, which are the same problems that we're still solving now. We want to go after fluid dynamics problems, weather modeling. They wanted to build an AI computer. They wanted to do the things that we are doing today in a faster way and go after the next set of data problems. So what's the software that you write for this kind of machine? Well, they learned all the pain from the 60s and 70s as well. So I'm in that phase of I want to accelerate the novice. Fortran has become canon at this point. I think around this time, Tony Hoare says, I don't know what they'll be writing in the year 2000, but it'll probably be called Fortran. I think I was talking to some people today who are still working with Fortran. There's thought like that has not died. It is still a very useful tool. And this is in between, so this is in the 80s, this is in between Fortran 77 and Fortran 90. So rather than teach people or have a whole new sense of software, we'll just basically invent vectorized APIs. Like, these ideas had been written down. So rather than writing nested for loops, which you can only do in Fortran 70, we'll introduce new ideas for the engineer, like matmul, dot sum, for all. These things that we do a lot in NumPy, right? We don't write for loops over NumPy. We write this vectorized version of NumPy, and those origins start here. Sorry, just to tell you a little bit more about this machine. You give a programmer an LED display, and they want for animation. So the lore is that at the end of this LED display, it's showing you whether or not you're using that particular processor. It's a lot of the warm, fuzzy feelings that many of you will get when you want to see high GPU utilization. So the ideal state is this is just a infrared light just shining at you. So the lore was, at the end of a job, you would specifically design some wonderful messages that would appear on these displays. And people like NCAR and like L&L, like a lot of national labs picked up this particular machine Yeah, I really wanted to tell people about it because it was unexpected. Have you ever seen Jurassic Park? It was the machine that powered Jurassic Park. Although in the book it's Cray 1, but this is the machine that controlled all the dinosaurs or kept them in their cages. But we're at this place of, well, how do I think about software to run on specialized hardware, or how do I make any of this software leverage these complicated things? And in this time period, a bunch of computer science and implementing these ideas takes place, where we have caching algorithms and tiling algorithms. All these things get written in canonical texts that I've never read, but I'm the inheritor, so is everybody here, of these ideas called numerical recipes or BLOS. And these things eventually bubble up into NumPy that we can take advantage of. And NumPy is on this axis of extremely easy to use. I had really never heard of BLOS until probably like 2 or 3 years of being an employee at Anaconda. I just used NumPy, ignorant of what it took to actually make those things possible, but I was able to move on with my day because all these people wrote down all this work. They implemented it in C. Travis and the entire NumPy community wrapped it all up in a package, and then I didn't even have to do anything to compile it on my machine. Like the pip and conda engineers made it so wonderfully easy for me to use my machine, and use my machine quite effectively. And during this time period, I at least learned a little bit more about how modern computers now are laid out. So we think of, or at least at the time, I'm going to bounce a little bit back and forth in history, but at the time my thoughts were what a computer looked like was something basic. Maybe you can call this a von Neumann machine. Maybe I think of it as like the Bohr's model of a computer. It's not all models are wrong, but some models are useful. And this was useful for me, at least in terms of understanding how a computer works. There's disk, there's RAM, and there's CPU, but it's not that simple, right? There's a cache on the CPU. I can store a little bit. If I've already gone through the pain of pulling some data from RAM, I can store a little bit of that on the CPU. And there's not just one CPU, there's also multiple cores. There's not just multiple cores, there's lots of sockets. So when I come back to NumPy, again, it's this really wonderful experience. NumPy takes advantage of all those things. It scales. I add another core to my machine, and it magically figures out how to appropriately BLOS, figures out how to leverage all the cores on that machine. It's a really wonderful experience. If all I needed to do was linear algebra, that's like the gold standard of what you might want to go after. But not everything is linear algebra. Okay, so I'm going to jump a little bit. It's awkward. I had a hard time with this transition. I wanted to at least motivate this before I get into the next set of things. Like what happened in the 80s and 2000s? Well, the personal computing revolution took place. Everybody in the world bought a computer. They put one in their kitchen. They put one in their house. I had 3 in my dorm room. Trying to figure out if I need to embarrass myself. Is there anybody here who has perfect pitch and wants to sing these 4 5 notes? Does anybody know what those 5 notes are? Yes. Okay. All right. I'm still going to do it, but thank you. I've never sung in front of an audience. I believe it goes bum 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 bum. And that was the advertisement across everything. That was the Intel Inside advertisement that everybody heard from 1990 well into the 2000s. Everybody bought a Pentium 3. Eventually, you bought a Core 2 Duo. We were in the heyday of Moore's Law. Everything is just doubling and doubling and doubling, and life is just so great, except for those few kids who decided to overclock their machines in hopes of a faster And then things got weird in terms of data. Things got really weird. Like the world exploded in terms of data problems, and a bunch of people at Google and Yahoo, they write down this paper called MapReduce, and when those folks went around searching for problems for how to go after this explosion of data, they didn't go to specialized hardware, right? All of us here drove the market to bring down the cost of chips and silicon. So instead of building some specialized machines, they decided, very similar to that connection machine, how do I aggregate a bunch of low-end commodity off-the-shelf hardware and put it all together and write software for it in a way that actually lets me solve my problem right this minute. And it brought in a whole wave of structured and unstructured data. All of us were talking about Java for a while, and eventually SQL came back, but we exploded the database because those databases couldn't quite keep up with what was happening in the data world. And it wasn't just Yahoo and Google. During this time period, at conferences like PyData, they were saying weird things. They were saying things like, that's not a financial company, that's a data company. That's not healthcare, that's a data company. That's not a farm, that's a data company. Everything became a data company, and everybody was building data applications. And they all got on this Hadoop bandwagon. Rightly or wrongly, this is like how the world kind of moved. But these HPC experts, like, kind of sneered, or at least in a few conversations that I had with people, kind of sneered at these things. And you can see some of these inefficiencies. You take a bunch of low commodity hardware, you connect it up with Ethernet, and you start thinking about inefficiencies. Right? These aren't what are referred to as fat nodes. These are kind of small nodes. You have to pay a cost of moving data around. You have to pay a cost of moving data onto these machines. There's a lot of cost, and HPC folks had been spending the last, they moved on from the connection machine, yes, but they have been spending the last few decades really tuning all these machines and influencing the hardware design of how to build high performance clusters. But a great thing happened to me. NumFocus was started during this time period. All of us, like the world, for me at least, was really great. PyData gets created. This is the original NumFocus slide. If you see Leah Zaitlen around, there she is. Yeah. Today, this is her last PyData conference. We should all be thanking her for all the things that she has done to put all of this together. So all of us got, like, NumPy was this great thing, but all of us got together and built this wonderful, wonderful world. Maybe you can call this PyData Classic. And all of us were moving pretty fast, and many of us said, oh, Panda doesn't work on your single machine. On your machine, just go get a bigger node. Like, the cloud exists almost at this, or definitely exists at this point, and you can just go get more RAM, you can go get a faster processor. But there's a little bit of a problem. There's two problems, really. One of the problems is that Moore's law is struggling. I'm not so confident or so grand to say Moore's law is ended or anything like that. But at least in terms of single-threaded performance, things are not doubling the way that we had wanted them to in the past, or the way that we expected them to. We got hooked on these ideas in the 80s and 90s. And the other thing is that our architecture was more complicated. Like, now everybody has a multi-core machine, and everybody's using cache. But not, as I said before, not all those problems were NumPy problems. So I guess this is the audience participation part. If you were alive and a Pandas programmer during this time, how many of you wanted to build a distributed group by? Sorry, how about a multi-core group by? Okay. All right, there's handfuls. So many people went to multi-processing, and you can write down what your groups are going to be, figure those things out. You do an aggregation, you bring all that data back, you do a local aggregation. And that was like how we initially started leveraging the actual machinery inside of our laptops on cloud infrastructure. And the second, I don't know what to call this, maybe we're still in it, the second wave of PyData maybe is happening, where a lot of the tools that were just starting then, where we canonized like these multi-processing ideas with things like DAS or Ray, but maybe now we're thinking about how to leverage these hardware for non-NumPy things like DB, controllers, where we are using all the cores in our computer. We're thinking about caching algorithms again for other things. We have this advanced architecture that we can take advantage of. We have to do maybe some rejection of APIs that exist, but this community is still like going strong after, we're going hard after those kinds of problems to get the performance that we want. And it's actually not just in the ETL space, right? It's really cool. Like libmamba comes around and makes my life a lot easier. Like it's way faster than a pure Python Conda implementation. And it's not just Conda, right? UV is this wonderful Rust-based implementation to make my pip package download that much better. So this community is still leveraging, still exploring how to do hardware things, but it's a little bit different than where we were before. Okay. So let's just briefly come back to this thought experiment. Can we reproduce this model? You know, maybe it's an interesting thought. I don't spend my days doing a lot of model work because I'm busy with other topics. I have other problems. You know, my problems look a lot like these kinds of problems. I'm spending more of my time thinking about business problems or scientific computing problems, and we're in this space again of data explosion. We have instrumented way more of the world than we possibly ever did or ever thought we could in the past. So those weather modeling problems in the 80s, we're still doing that. We pointed any number of satellites down on Earth to look at any number of things, hopefully mostly good things. We've instrumented every factory. We've instrumented ourselves. We want to be able to do the things that we were doing last year and the year before, but we want to do them in a second, in sub 100 milliseconds, in sub 10 milliseconds. How do we possibly solve this kind of problem? What is the hardware that we should be building to go after this problem? Right? The last decade, we scaled out low commodity hardware. In this decade, my argument is that we're making things way more dense. We're going to contract that Hadoop cluster into one big cluster. This part of the talk is going to be a little bit producty as a heads up, but these ideas extend to lots of people that are exploring this space in the same way that the hardware that was being developed in the 60s and 70s was done by lots of organizations and lots of people. These same ideas are out there. They're not necessarily unique to any one organization. That's just a heads up. And now for the producty parts. All right. So NVIDIA sees this problem. And many people here, if you attended any of these talks before, or maybe you've thought about it using a GPU in the past, you're told it's really expensive to move data back and forth between host and device. Does that sound familiar to people here? Yeah, it costs a lot. In 2016, NVIDIA releases, again, this kind of connection machine-like thing. Here is the AI computer that you should be using. And we've packed a whole bunch of things together. So it's not just one GPU, it's 8 GPUs, and it's 2 islands. So if you can figure out how to run software on this architecture where most of the data, most of the compute is happening on one of the islands, or one of the 2 islands, and there's not as much communication, your life will be pretty grand. That's challenging to do. Not everybody can do that. There's a whole bunch of software that has to be written in order to make that happen. You need to learn a bunch of CUDA things, but people do, and they're quite successful. There's some numbers on the side just to make sure that I'm saying reasonable things, but mostly what I want to impart on you all is that the idea here, the game that we're trying to play, is keep data on the GPU as much as you can. Don't move back and forth. And with 4 of them that are interconnected with this technology called NVLink, we don't have to pay a lot to move data between those GPUs. Does everybody follow me so far? Okay, so what's the thing that we should do next? Well, I mean, without being a hardware expert at all, it would be, well, can I be greedy? Can I just have instead of 4 things, instead of 2 different islands, can I just have, all of them together? If this was just like, if we were civil engineers, we'd say just go build a bigger bridge. And that's what NVIDIA does in when does this come out? 2021, maybe? More recently? So the individual units are getting faster. We expect things to get faster. We expect things to get bigger. This is now we've gone from like 32 gigabytes to maybe 40 gigabytes, 80 gigabytes. But the thing, again, that I want to impart on people here is that we highly interconnected all the GPUs together. So now we don't have to pay a cost between moving data back and forth between those two islands. It's a wonderful experience if you can get to this place, if you can make the jump over, where you're not moving back and forth. So then you think to yourself, well, what's the next thing that I should do? Well, I want to be greedy. Can't I be faster between moving things between host and device, between CPU and GPU? And the answer to that question is also yes. That there's a bunch of hardware technology and hardware engineers at NVIDIA and many other places that are saying, well, yeah, I could just build dedicated lines to move data back and forth. So the memory bandwidth of these things that are going up, sorry, that's what I was saying before. So these individual units, the individual GPU is getting bigger, it's getting faster, but the memory bandwidth is getting significantly faster. That thing is increasing in a way that helps me, in a way that I couldn't really think about before. It presents these new ideas, maybe not new to some people, but new to me, of these ideas of coherent memory. If I don't have to pay such a high fee of moving back and forth between CPU and GPU, then I can explore this space where data lives simultaneously between those places because there's no cost anymore. What new problems can I go after? I was a little bit more confident, I tell you, about join reordering. Some people are very excited about that. That's a very expensive computation that you have to think. Your engine has to do a bunch of work to make that happen. But if I can move back and forth between CPU and GPU, I can do all these fancy sorts. I can collect different ideas that I wasn't able to explore actively. And then maybe NVIDIA goes really hand over fist and takes this idea and really explodes it out. How do I string up many GPUs together? I think this is 72 GPUs and 36 CPUs, all highly interconnected. And you look at these problems, you look at this kind of infrastructure, and you have to immediately ask yourself, how do I control it? What is the software that could possibly run on that kind of infrastructure? Not everything is PyTorch as much as it should be. I might want it to be. I want to do it feels weird to say, but like maybe classical machine learning. I don't want to do just deep learning. I want to do a random forest. I want to do a linear regression. I want to leverage all of that hardware. So within Rapids, we've been building towards that for quite some time. And thinking about those two axes of ease of use and speed of light performance. This is a term that gets thrown around a lot at NVIDIA, probably in a lot of HPC places. Speed of light. I want to go as fast as possible. And we built, the thesis of Rapids was go all the work that we all agreed on by consensus. That PyData stack of pandas and NumPy and scikit-learn, we'll use those APIs and we'll do all the work of building accelerated versions of them. And we're in that space of well, it's like those libraries, but there's some edge cases, right? Not everything, as many attempts as there were at people building a faster pandas. We tried to do the same thing, but there's still some oddities, there's still some edge cases. It's not quite there, and it's hard actually to get adoption if it's not one-to-one. It's not perfectly one-to-one, right? This community does prize performance, but there's also speed of light usability, maybe to adopt that term, right? We want things to be very ergonomic. We prize computer time, but we prize our time more than that. So we're domain experts. We're going after all these different problem domains, yes, deep learning. But again, thinking about that connection machine of I want accelerated DSLs. How do I extend what I currently understand in order to go after this contracting hardware in a new programming paradigm? Can I get that? And the answer to that question is yes, as well. So in the last year, we've been very actively exploring how to do literally zero code change. So Many of you probably in the last 5 years were at some point told to import foo as PD. See how it runs. I told people to do that many times, and I regretted that. So we have some room to play here. We can give up a little bit more performance and going after more usability, and think about how we can onboard more people onto this kind of accelerated hardware. So we have PDF pandas and Network X. Many people here talked about it. See the NX cuGraph talk. In a little bit, you'll hear about what we've done with polars. Richie, if you're in the room somewhere. No, that's okay. Yes, we're giving it performance, but there's like actually this onboard ramp, this new programming paradigm, new hardware paradigm where everything is already taken care of for you. But it's still exceptionally higher performance than the tools that run on CPU. And the reason that this works is because of everybody here. We all are thinking about how to work together. It's all this community of how we're all interacting and agreeing on everything. It is not we all are spreading these ideas of PyData within this kind of wonderful, chaotic bazaar. And you should be pushing on tool developers to leverage that kind of infrastructure. Don't make me go learn something else. Keep me where I'm comfortable right now and start building towards that. At the same time, I think people, if you heard Bryce's talk earlier, are exploring ways to onboard people that don't want to go all the way down to the C or C++ world, but want to explore GPU computing entirely from the Python side. So perhaps you've seen that swim lane picture, trying to figure out how to meet people where they're at. So we're exploring all these developers and all these users, and it only works because all of us are kind of working together in concert, and Rapids is trying to be a part of that community. Yeah, so when I see what's happening at my employer, but also what's happening in the world, I see this contraction happening in lots of places, right? It's not just happening to GPUs. This world of, I feel very lucky that I lived both in that x86 homogeneous dominant period where things were pretty great, but I also get to experience this like Cambrian explosion of hardware again, right? It's not just GPUs. There's NPUs and TPUs and IPUs, FPGAs sometimes rear their head every so often. I can never wrap my mind around how to actually program for it, as much as I might want to. But we see all these things coming together, and we know how to actually make it faster, how to pipeline data correctly, how to increase memory bandwidth to these accelerators and build these machines that are going to be more and more common. Right now, you can go to any cloud provider and go get a 32 terabyte, 1,000 core machine. That's a dense machine. What problem can you not solve on that machine? And there's definitely petabyte and zettabyte, sure. You can go get a 640 gigabyte GPU, and in the future you'll be able to go get a 1 terabyte plus machine. Between 1, maybe 2 terabytes of GPU memory and 3 terabytes of CPU memory, what problems can't I attack? This, I think, right now we're in this age of density. I'm not willing to make any pronouncements about the next decade. Maybe we'll scale this all out, and we'll all be talking about the next, Hadoop X.0. Yeah. So thank you so much for letting me tell you about some of the computing history. I really appreciate it, and thank you all for being here. It's been really fun.